So yeah, hi. My name is Dan McIsaac, and I'm a professor of physics at SUNY Buffalo State University in Buffalo, New York. And I'm going to briefly present and talk about a method for collecting a video portfolio of students solving physics problems. And the idea is that students each create this portfolio, and in my courses, it replaces a weekly Friday quiz. So this is kind of old wine in a new bottle. My classes at the university are for algebra trig-based physics, are the examples I'm going to show you here, but it can be done with any level. I teach in a 16-week semester. Usually there's a week off and a week for final exams in there. So we usually have around 11 Friday quizzes. We take one Friday to do a personal introduction, and I usually have a practice quiz. And I usually take the best 10 grades of the quizzes and drop the lowest 1 or 2. The quizzes are worth, these videos, portfolios, are worth 10% of the student grade, all in all. I also use the same system to collect 2 problems for each of their exams. And these students will have one midterm and a final exam, so they do 2 exam problems on the video portfolio system as well. And many, but not every semester, I have my students also do a group video project where they do a physics experiment and explain it and document it. And that takes a little longer. That's usually worth about 15% of their grade. But when they do that, I collect those via this same system. The system I use is called flip.com. At one point it was called flipgrid.com. It's a really valuable system for collecting and collating and curating student videos. So you don't have to have it on your own campus, although you can link to it. It's free. It's currently owned by Microsoft, and there are apps for cell phones and tablets as well as laptops. And I encourage my students to use a laptop, but certainly every student can use a cell phone to record themselves solving a physics problem. Let's have a look at this. So this is one recent class that I'm looking at here, Physics 107 from fall 2020-21. In here there are a whole pile of quizzes. You see them labeled quiz 1, 2, 3, 4, 5. This is a midterm exam long question 1, midterm exam long question 2, and they had a 90-second introduction. So they usually get this introduction in their first week. I show it here. There are 18 of these things. These video assignments can be set out in multiple ways. You can shoot a short video where you're showing them what you'd like them to do, and that's what I do with this 90-second introduction. I introduce myself. If you click here, you can see me introducing myself in the video. This is a list of the things I'm looking for. Use your laptop or smartphone to make a short 90-second introduction. You're supposed to have your full legal name, including how to write and pronounce it, and you need to hold a piece of paper up showing that information so I know that the students can get diagrams and text correctly left to right, because later on in the course it's going to matter very much because I'm going to be reading what they say. Also, I get to check their sound. They're supposed to mention their year and major, background, hometown languages spoken, and then something tasteful about themselves and memorable and publicly shareable. Then they're supposed to watch the video to check the quality and clarity. Now, the students actually don't usually get all those things. When I grade these things, I grade them very much on a process approach. Are they following the process? I'm more interested in the process than the products. So we'll watch an introduction here and see what they did. But mostly they get, most of the points for it. It's very typical for these things to be graded 8, 9, and 10, mostly on completeness, and although some students might not do it. Okay, so I'm looking for someone here that's obviously holding a sign and not actually seeing it, interestingly enough. This is not quite what I saw last time. Let's have a look at this woman's intro.
Hi guys, my name is Cheyenne Cook. This is how it looks.
Okay, so Cheyenne here is holding up her name and text, telling me how to pronounce it. She's obviously ahead of the curve. She's actually done what I asked her to do. Many students don't. And this would pretty much be a 10 right there.
I'm a senior here at Buff State. It's my 3rd year, so I'm graduating early. I have a major in psychology and a minor in criminal justice. I plan on going to medical school in the fall, which is why I'm taking a bunch of science classes so that I can go to med school. I am from Buffalo, New York. I only speak English, and something memorable about me is that I usually work in between 35 to 50 hours a week, and I also have 10 piercings. I plan on getting more, so I'm not sure if you can see, but I have 3 on this ear, 6 on this ear, and then on my nose.
So this is a fairly typical.
Hi guys, my name is.
So a fairly typical student, although clearly a 10 out of 10 on the first project. By collecting these introductions, the students go back and watch one another's introduction in the class, and it's a very big deal for promoting a class culture. So I have them each create a video, and in some cases it's not unusual. In this case here, this gentleman named Dante has recorded it twice. He didn't like the first version, so he recorded a second one. These are all hidden until I publish or expose them to the rest of the students. So he put in 2, and he sent me a note saying, use the second one, not the first one. And so it's pretty common if someone doesn't like the job they did the first time for me to share the second one. And if a student, for instance, solves a problem, doesn't like the solution they did the first time, then we count the second one. I'm good with that. Usually we have time for that, I guess I should say. I guess we were looking up here. Okay, so let's look at a introductory practice quiz. So here's a practice quiz. Not everyone did it. Notice this due date is up here as well. This is a classic introductory physics activity where the students have to basically convert between units. So in this case, they're doing unit conversions. This was shot during COVID. The problem was developed during COVID. It's the growth of my beard speed during COVID from September to February. Basically, it says show your face on camera, state your name on my roster, and your month of birth, MM, your month, is a 1 or 2 digit number, and we'll see why in a second. So you're supposed to do the pandemic beard speed quiz. Since September, Dan's beard grew 5 inches in 5 months. So you have to find out what is the speed of Dan's beard growth in millimeters per day and miles per hour. Show and explain your conversion calculation. You have 90 seconds, so it has to be brief. If your own hair grew at mm divided by 6, so if you were born in December, mm divided by 6 would be 12 divided by 2, which is, 12 divided by 6, which is 2. Inches per month, how fast would it grow in millimeters per day and kilometers per hour? You don't have to show your work for the second part. Check your video for sound watchability. Okay, so let's get someone here who did this.
Hey guys, Phil Speed here. Let's see what we got. All right, Professor Ding.
Okay, so now you're seeing how important it is to be able to get the text left to right.
5 inches in 5 months. That is 1 inch in 1 month. 1 inch equals 25.4 millimeters. 25.4 millimeters divided by 30-day average is 0.85 millimeters a day. Good for him. For miles per hour, we got 1 mile equals 5,280 feet. 1 foot equals 304.8 millimeters. We also have to figure out how many millimeters his beard grew in the 5 months. So there's 5 months times 25.4 millimeters, which is an inch, over feet in a mile and millimeters in a foot. So then we get to 5,280 feet times 304.8 millimeters. And that gives us 1,609,344 millimeters in a mile and 127 millimeters that his beard grew in the 5 months. It gives us the grand total in miles per hour of 7.9 times 10 to the negative 5th power. My birthday month is 8, so we got 1.12 millimeters a day that my fake beard grew, and in kilometers an hour, it grew 1.7 times 10 to the negative 4th power. Now I get to have that.
Okay, so this is a student who's done well, but hasn't done a perfect job of it. He's missing some things, but again, it's processed, so he's going to get most of the credit. I can send back through the system, I can send back a note to him saying, you know, you got so many points for clarity and visibility, viewability, your video was excellent. Here are, however, you need some extra work on conversions, particularly time conversions didn't work out. This is a kind of a problem where they can actually ask Siri to check their calculations, but it's a skill that they're going to need for the entire course. This particular problem, where it can be solved 12 different ways, I have a solution spreadsheet online, and when I assign these things typically on a Friday, and then I collect them. Usually they're all due in before the following Wednesday. I usually teach 3 times a week, including one Friday. So it's either Tuesday, Thursday, Friday, or Monday, Wednesday, Friday for these students. What happens is I give them the quiz on a Friday. It's assigned, and they sit in a room and they work on the general quiz together in small groups. And they have 15 minutes typically of class time. It's the last class for the day, usually for them on Friday, so they can hang around after class if they want to and continue to work on it. They don't have to. But they get some class time to discuss it and work with one another, and I think that's perhaps the most important time for their learning, is that small group discourse. Then what happens is they each shoot their own videos with their own specific numbers for their own specific case, which is somehow keyed to the month and date of their birth. So what happens is I freeze the system so they can no longer submit things, usually the following Wednesday, sometimes the following Monday, and I put up a solution online through the class LMS, Learning Management System, and it has a spreadsheet that has all of the solutions for all of the dates, and it usually has a still image of the problem. And so in this case, he wouldn't have received full credit, but he would receive a chunk of it. And feedback, the feedback is private. For really good solutions, I would ask their permission to share them with the entire class. But they can always access it. But it's available to, they're always available to me, and if it's a really nice one, I will publish it so others can see it. For instance, in this case here, Jeanette's solution here is visible to the entire class. It's not hidden. She probably did an excellent job and got 10 out of 10. Okay, so I want to show a more advanced problem. Okay, here's a hanging sign. This is a classic kind of problem. Let's find someone here who creamed it. Diamond probably creamed it.
Here we have my free body diagram for the sign. So the force of compression is pushing it to the right, and then on the left, at an angle, is the force of tension.
Okay, so in this case, they were given a free body diagram to work with and to analyze, or they were given, I should go back here a second and look at the problem. In this case, the problem is a statement on a piece of paper. It's a sign hung from a particular angle. There's one of these actually on the road near campus. And they're supposed to draw a free body diagram and calculate tensions, etc., in the thing. So in this case, it's a problem statement.
Here we have my free body diagram for the sign. So the force of compression is pushing it to the right, and then on the left, at an angle, is the force of tension. The force of tension
She drew it up here.
has
There's compression
a
in the
y
bar.
and x component. And then pulling it downwards is the force of Earth's gravity on the sign, also known as the sign's weight. Newton's second law for the pin, both the x and y directions. So for the x direction, we have the force of compression plus the force of tension in the x direction is equivalent to 0 newtons. And then for Newton's second law in the y direction, it would be the force of tension in the y direction plus the weight of the sign is equivalent to 0 newtons. The force of tension is equal to 770.2 newtons in the upward direction. The force of gravity is equal to negative 590 newtons in the downward direction. And the force of compression is equal to 495 newtons to the right, or the positive x-hat direction. The force of tension is the highest magnitude compared to the weight of the sign and the force of compression.
As far as the force of compression in the steel bar, it is lower than the magnitude of the weight of the sign. The values seem reasonable, and the units all seem to be acceptable.
Yeah, so she did an excellent job. That's another 10 out of 10. And so they're the classic kind of touchstone activities that you would expect to see in an introductory physics course. Plotting XVA graphs. I have one where they watch a video of constant velocity buggies moving in different directions. They're asked to collect data from the video and plot it. In some cases, they watch a clip from a science fiction movie and do it. In another case, I have a lady physics professor from UPenn laying out a very non-traditional problem that she's actually studied physics professors solve that they can do on angular momentum. So it's very nice for them to see a female of color physics professor giving them a problem. And there are, kind of classical problems. Ladder problems are very classical kind of problems for teaching torques and frictions. In this case, the problem is difficult, and it's kind of like learning to play a scale on a piano. So it's worthwhile for a musician, for a pianist, just to be able to bang their way through the scales. And I'm not so worried about authenticating that the student can actually do this cold without notes, so much that the student can at least talk their way through it in a complete fashion. So much like you would have a piano student bang their way through a scale, I have the students, they can bang their way through these ladder problems. Here are some examples of others on the internet solving the ladder problem. Here is a link to this picture. The picture here is partially complete. It's not fully complete, but it does label some forces, not all of them. They have to complete an extended free body diagram from this and do this. In this case, the angle of the ladder with respect to the floor is 55 plus XX degrees, where XX is the date of their birth from 01 to 31. So in this case, if I was born on the 15th, for instance, my angle would be 70 degrees because it's 55 plus 70 degrees. And then in this case, it's a classic problem. And for this one, in fact, a variant of this problem is then again asked to them later on a on their final exam. Okay, so what can I tell you about doing these things? Some of the students really love them. Some of the students really hate them. I think they're less stressful on the students than getting them to stand up live in front of a room and solve a problem on the board. It certainly is a high enough stakes thing that they really do want to work in their groups with one another to figure out how to do this. They are very driven by it, and it's something that they all experience together. So having this video portfolio can be helpful to the students if they're applying to medical school or they're applying for an internship. It can be a valuable thing, particularly for the extended video project. And I can show it to my colleagues. And if we can't meet live during COVID, we can do it online, although even when we can meet live, they still wind up doing it. And I still think it's a fruitful thing to have my students do, and it provides me with an opportunity to give them credit for hard work figuring out physics.